Hi, I'm Jim Harris, and I'm going to give the next talk here on SPDK Tracing. How do we build a framework to keep up with these millions of IOPs? So, the agenda for my talk today, I'm going to talk a little bit about how to enable the tracing framework in an SPDK application. How do you actually view this trace data? So we'll kind of start off on just how do you enable it and actually use it. Then we'll take a step back and look at the overhead of the tracing framework, talk a little bit more detail into the architecture. So how do we actually capture this data? How are the files laid out? How are they consumed by the tracing apps themselves? Talk a little bit about some of the shortcomings of the tracing framework and how bpftrace can be used to mitigate or supplement the SPDK tracing framework. And then I'll share a few tips and tricks. So before I get started, just kind of want to lay out the problem statement for a tracing framework, especially for something like SPDK. So we have these applications that can achieve millions of IOPs per CPU. We want to make sure that we have a tracing path that matches that level of performance. And so there's really two avenues that we need to be concerned about. So first is we want to make sure this tracing support can be enabled in all builds. We don't want you to have to rebuild your application to get tracing support. You should be able to have it enabled in a release build and have minimal impact when tracing is actually disabled. But then when you do enable it, there is going to be a certain amount of overhead, but we want to make sure that that performance impact is minimal, because one of the primary cases you're going to be doing this is to capture traces during benchmarking, high I/O workload test cases. And so we kind of say what the overhead goal is. I think we can say like 10% degradation on a performance workload is probably reasonable. I mean, you're going to get a little bit of a hit, but it's not going to affect it so much that it makes the tracing data invalid or not usable. And so when we kind of work out the math, if you're doing, let's say, 2 million IOPs on a single core, it's about 500 nanoseconds per IO. If we have 10% overhead, that means we can't use more than 50 nanoseconds for 2 trace points. And I say 2 trace points because typically when you're capturing these types of traces, you have 1 trace point for the start and 1 for the end. And so that's going to be our goal, and I'm going to show how we match up against that goal later. Okay, so first, how do you enable trace points in SPDK? So the trace points are all grouped by module. So not every module in SPDK has trace points defined, but a lot of the primary ones do. So for example, we have ones in the generic bdev layer for start and stop for IOs. We have ones in the bdev NVMe module. We have ones down in the NVMe driver themselves at both the PCIe and the TCP transports. We have ones in the thread library. There's a few others. These trace points can be enabled in any SPDK module. It just takes somebody to take the time to go in and define the ones that make sense. At any point, you can get the groups that are available by getting the help. They'll always be in the application help if you pass -H to an SPDK application. So there's a couple of different ways to actually enable them. Probably the easiest one that most people use is just doing it at application startup. And so you just pass a -E option with a comma-separated list of the the trace point modules that you want to enable. So in this case, we're saying we want to enable NVMe TCP trace points and bdev trace points. But you can also enable and disable them at runtime. There is a JSON RPC to be able to do that, and you use the bdev names for that too. There's RPCs to both enable and disable one of these trace point groups. And so here we can look at this in action. You see here we're starting the SPDK target. We're enabling these two trace point groups, NVMe TCP and bdev. When you do specify these, you'll see some extra output from the SPDK application. This will be important for our next step because this basically tells you the application now is capturing trace data. If you want to go view it either now or later, here's how you get access to it. So next, how do we actually view the trace data? So we have an application in the code base called SPDK Trace. You can see there where the source code and where the binary lives once it's built. This application interprets the shared memory trace point file that the SPDK application has generated. It can interpret it while the application is running. It can interpret it after the application stops. So you have the, if you look, if we go back to the previous slide here, we can see that it points to the shared memory file in the file system. We can get access to it. But you can also take that file offline. You could compress it. You could attach it to a bug report, send it by email. So you have a few different ways of when and where you can actually interpret that shared memory trace point file. And so what this means is that everything you need to interpret the file is embedded in that shared memory file. You don't need access to the binary that generated it. The binary, the application actually puts everything that's needed into the file itself. We'll talk into more detail on how that works, but for example, it puts the names of the trace points. What are the relationships between the trace points? So for example, you may have an NVMF TCP request that generates a bdev IO, and so it can save relationships between those and how the trace application should be able to interpret that data. And then also object types and their lifetimes. So for example, it knows here's an object that's a bdev IO. This is the event that marks the start when that bdev IO was created, and then any other trace points that are associated with that bdev IO. It allows us to be able to offline be able to capture deltas from when that object started. And so here we look at the output of this SPDK target application that we've just started. We can see a few things here. So we can see first the core number. So it will capture what was the CPU core number that generated this event. It'll capture the elapsed time in microseconds. So the trace files only record the TSC because that's very easy to capture. It does not try to calculate any time deltas. Any time deltas are all done offline. And so you can see that the TSC rate is actually embedded in that file, which allows the application to then capture these time deltas. And these are always captured in microseconds. We can also see here that it's identified this bdev IO that was started. It gave it an identifier I9. We can see type 1. So if you go into the bdev code, you can see like what the type is. In this case, I think that's going to be a read. There's probably some stuff we could do here moving forward to actually embed better names for these, but at least it tells you what the type is. You can look that up offline. But the really interesting thing here is now it tells you when the bdev IO was actually done. So in this case, I'm running a really simple test. It's just a null bdev, so you can see it completed in 417 nanoseconds. So it completed very, very quickly. But this is really useful when you're looking at longer traces because you can see, this bdev IO started here, and then it ended way over here, maybe 820 microseconds later. And so all this stuff is this post-processing is all done by the SPDK Trace application. And then for each of these trace points, we can have specific data, arguments that are specific to that type of trace point. So for example, for a bdev IO, it makes sense to store the LBA offset and the LBA length of that IO. And so these are parameters that are specific to this trace point, and those get output as well. Okay, so let's look at the overhead measurements. So we're going to kind of use some worst case scenarios here. We're going to try to pump as much I/O through the SPDK application as we can, and just try to measure out of capturing all these events, how much time did it take, and kind of backtrack and figure out what's our overhead for each of those. So we're going to run the bdev perf application with both null and malloc bdevs. Malloc is our RAM disk block device. We're going to do queued up 32 512-byte reads. Of course, for a null bdev, you're not actually reading any data, but for the malloc, there will be a 512-byte copy in there. We're just going to do this on a single CPU core. I ran these tests on a Xeon platform in our lab. And then we're going to enable the bdev trace point group. So for each of the IOs, we're going to get 2 trace point events, one for the start and one for the end. Okay, so we talked about those two performance vectors that we're concerned about. The first one is how much overhead do we have just compiling in the support for trace points into the SPDK application. So there's no way, you actually have to modify the application to the source code to be able to do this test because it's always enabled. There's no way to disable it today. So I modified the application to remove the checks for the enabled trace point. So every time we have an SPDK trace point call in the code, we check to see if it's enabled. And so I just removed that check and ran some comparisons with the baseline code base. And so for the null bdev test, we effectively had a difference of less than 2 nanoseconds per IO, which means less than 1 nanosecond per trace point event, just for doing the check to see if the trace point is enabled or not. And then for malloc, it actually ended up being even less. It works out to just far less than a nanosecond per IO. So I think with this we can say we have effectively made this. There's virtually no cost to having this enabled in the code base. This is really in the noise. But the more interesting one is what's the actual cost when we enable the trace points themselves. So in this case, we're going to have the baseline, which is just running the test without trace points enabled at all, and then we're going to run the same test with enabling the bdev trace points. So for every IO, then we get 1 trace point for the start and 1 for the end. So of course here we see a much bigger delta when we work the math out. It's around 52, 53 nanoseconds per IO, which means 52, 53 nanoseconds for those 2 trace point events. And then it looks very similar for the malloc bdev, 55, 56 nanoseconds per IO. So I think we can say here our goal has almost been achieved. We didn't quite hit 50 nanoseconds, but it's pretty darn close, which means at least for some of these configurations, we can expect a 10 or 11% degradation if you're, basically capturing 2 of these trace points per IO. We're looking at some more optimizations. I think there's some possibilities for us to squeeze this a little bit more, but this is a really good starting point, and it makes this really usable for a lot of our performance workloads. So next, just looking at sort of like the architecture overview on this. And so this really is all based around the shared memory file layout. And so we have this structure called SPDK Trace Histories. This is defined in that header file shown there. And this really defines the layout of that whole memory file. So basically, on the application side, it's going to open this file. We're going to mmap it. We're just going to write data to it. On the SPDK trace side, it's going to do the same thing. And so byte 0 in that file points directly to this SPDK trace history structure. So then at the beginning of that file, we have SPDK trace flags. And this is going to describe all the valid trace points that we have in this application. So it'll say we have 1 trace point called bdev IO start. We have another one called bdev IO end, and it's going to go through all of those. And then it also describes the valid trace objects. So if you remember back looking at the SPDK trace application, how it showed, it knew bdev IO start, bdev IO end, and it knew that those were both related to a bdev IO. And so we have the ability to describe those objects, bdev IOs, NVMe requests, NVMe TCP requests. So it can describe characteristics of those objects so those can be processed offline. And then it also has an offset to each CPU's history buffer. So it'll say the offset 0 if that CPU is not used by the application. We don't want to allocate one of these history buffers for CPUs the application isn't using. So we just set that offset to 0 to say, like, yeah, we actually don't, we only have these CPUs, these other CPUs, we don't have any trace data for. And then after that, we have one of these SPDK trace history structures for each of the CPUs. And inside of there, we have a circular buffer of a data structure called SPDK trace entry. And then it also has an index to the next entry that it will fill. And so that's effectively what's in these per CPU buffers, is just these circular buffers of the data points. So in digging into some of these structures in a little bit more detail, so for the trace points themselves, we have a name, so that gets put into the shared memory file, bdev IO start, bdev IO end, etc. The object type, so for each trace point, we actually record an object, like a pointer, and so we basically say, hey, for this bdev IO start, the object type is a bdev IO, and so then this allows us to be able to say all of these trace points are associated with a bdev IO, which will allow us to do some of those time delta calculations later. There's a Boolean called new object, and so this is how we know bdev IO start. When you see bdev IO start, that means that bdev IO, this is the beginning of this object. It's the beginning of the lifetime of that object, and so that allows us to say, okay, we have all these trace points for bdev IOs, but this is the one that says when it started, when it came into existence. And then we have something describing all the arguments. So for the bdev IO start, if you remember, we had arguments there for the offset and for the length. This is where we describe those. So we say, hey, these trace points describe these arguments. What are those arguments named? So that then later, when you process the file offline, you can print meaningful headers for each of those argument values. And then finally, related objects. So we actually have the ability in the SPDK tracing framework to be able to track. We had an NVMF request come in over TCP. That got passed down to the bdev layer, and we have a bdev IO. That bdev IO then generated some bdev NVMe IO in the bdev NVMe module, and then that went down into the NVMe driver itself and generated NVM requests. And so we actually have the ability to describe relationships between those objects, so that when you look at the SPDK trace, you can see here's where the NVMF TCP IO came in at the top end of the stack, and here's actually where it ended up going down to, like, let's say an NVMe SSD on the bottom end. So that's really powerful. And so then for each of these SPDK trace entries, this is that circular buffer we have on each core. And so first we capture the TSC, and we always only calculate the raw values. We don't do any type of delta processing in line. We let the post-processor, the SPDK trace application, do that after the fact. We capture the trace point ID. So we say this SPDK trace entry is a bdev IO start. The object ID, so we say here is the, basically the SPDK bdev IO pointer that's associated with this event. We have the arguments, so in this case we'll capture for this IO, it was offset 64 and length 8. That data, there's space, I think it's like 40 bytes of data that can be captured in each of those SPDK trace entries. Conrad Steiber did some really good work earlier this year to allow us to actually overflow. So if there are cases where an entry needs more than 40 bytes of data, like, we can do that. We can also have variable length strings and things like that in there as well, in a very low overhead way. So there's a lot of flexibility there that we didn't have a year ago. And so then how does this all work? So there's two phases. The first point is the trace point registration. And so this is basically where we are going to fill out all the data that goes into that SPDK trace flags data structure. So any module that's going to register, create a trace point group is going to have one of these constructor functions. And then inside of that constructor function, you're going to do a bunch of calls to register objects, register the event descriptions, and then also register the relationships between them. So where you can say this NVMF request is associated with the bdev IO. And so this allows us to be able to register all these in the modules that are actually defining them. And then later at execution time, we have two primary functions here. One is SPDK Trace Record, and then there's also SPDK Trace Record TSC. And so on some architectures, just capturing the TSC can be it can be noticeable. It can take a few nanoseconds to do, and so there are cases in the SPDK codebase where we already have the TSC. Why don't we just pass that to the function and use it there instead of capturing it inside of the trace library itself? So it just gives us a little bit of an optimization there. But then the code for actually checking if it's enabled is actually in line, so it's in a macro, and then only if it's enabled do we actually call into the trace library to do the recording. And so this is what allows us to make sure we have that very, very low overhead for checking, because that code is all in line. It's basically just doing a bit mask on a global register. Okay, so shortcomings. So one is, I mean, you always have to make explicit code changes if you want to add new trace points. So we have quite a few in the code already. If you ever want to do more, you need to add them in, which in some cases can be, a little bit problematic or cumbersome. We do have relatively limited types of analysis possible. I mean, I showed the ones, that were there, currently, but it's primarily capturing, time delta. So we have events and we can say, this event happened X number of, microseconds after this other event. But the types of analysis are mostly limited to that. So one of the solutions that we've identified for use cases that maybe SPDK tracing doesn't fit is bpftrace. And so I want to talk a little bit about that next. So what is bpftrace? It's effectively a high-level scripting language, very roughly based on awk and C, generally available as a package on most Linux distributions, and it allows both statically and dynamically defined probes. And it really lets us do a lot of very powerful kinds of analysis. We can do things like, maps, associative arrays. We can capture user stack traces. So when a trace point happens, we can capture what's the stack trace. That's pretty powerful. We can capture histograms in line. We can do symbol resolution. So if we have like a function pointer, it can actually resolve it to the name of the function. And we can capture kernel events too. So SPDK tracing obviously only applies to the SPDK application itself, but bpftrace allows us to, in a lot of cases, be able to see what's going on in the kernel as well, including system calls. So how do we use bpftrace with SPDK? So we've got in our docs USDT. This is user space dtrace. A lot of the bpftrace stuff is roughly based on dtrace that was originally in Solaris. This contains the instructions for how to install bpftrace. In some cases, you can use the distro packages. In other cases, you do need to build from source. We have a helper script called bpftrace.sh, which really simplifies using bpftrace with SPDK. So for example, when you're doing some of these probes, you need to specify the full path to the executable name, or insert the PID of the application that you're processing. And so this script basically helps automate inserting that into your script so that you don't have to, always type that information out every time you want to run an app. We have a number of example scripts in SPDK. I'm going to go through a couple of those today. And then we do have the ability to add custom bpftrace probe points. You don't have to do this in all cases. There's a lot of bpftrace things we can do without touching SPDK at all, but we can add SPDK dtrace probe to be able to use bpftrace with our custom probe points. So first, send message.bt. BT is sort of our bpftrace file extension. And so you can see the code for that script right there in line. What it's basically doing is counting the number of times that a couple of our SPDK thread APIs are used. So in SPDK, we have SPDK thread send message. So we've got two SPDK threads. We want this thread to send a message to this other thread. And so we're going to count how many times that happened, and then also SPDK for each channel. So for those that are familiar with how SPDK does per thread context information, there's cases where we can say, I want you to execute this function on each I/O channel for this I/O device. And so what we're going to do here is we're going to count how many times these APIs were called, but then also as part of that, capture what was the function pointer that we passed to each of those. So in this case here for SPDK thread send message, we're going to use an associative array, and the key is going to be the name of arg1, which in this case is the function pointer that we're going to execute on the destination thread. And so this is count just basically says increment that value by 1. And then similarly for SPDK for each channel, we're going to do the same thing, but in a different hash map for the name of the function that we're going to execute on each channel. And so then if we look and see, we run this bpftrace script, we pass it the PID of the SPDK target, and then this script goes and it executes this bpftrace. We can let it run. Once we Control C, once we break out of it, it's going to spit this out. And so we can see here for each channel, we can see that there were 3 different functions that were passed to it. This one, it was passed 1 time, this one twice, this time 7. Similarly, for the SPDK thread send message, we can see how many times each of these functions were passed. So it's just an example of a case where you can sort of see like what types of operations are, what types of cross-thread operations are happening within SPDK at runtime, and then also what are the for each channel, what are the cases where we want to iterate across all the threads to perform some operation. So next, this is a really easy one, but really powerful, is be able to count the number of times that each syscall is called by SPDK. And then print and clear that array every second. And so you can have this sort of like running on the side while you're running some workload, and you can see like how many system calls is SPDK making. And generally we try to avoid system calls as much as we can. But of course we're using the kernel TCP stack, and so we are making a good number of system calls, and so this just gives us some insight into the frequency of those without having to touch the SPDK app itself. And so if we look at this example, these are built-in trace points. These are actually exposed by the kernel, and so we can say for our PID, for our SPDK application, count, and so the probe is the name of the probe. So in this case, we have a whole bunch of different system calls. You can see the wildcard here. So we have one for sysenter readv, sysenter epoll wait, sysenter accept, etc. And so it's going to count each of those. And then here, every second, we're basically going to print out the associative array and then clear it, so that every second it'll reset and we'll get the values for the last second. So here we can see, so this is basically just running an NVMF TCP workload, and we can see here within this, this 1 second time period, we called epoll wait a lot. So in this workload, it called it 1.3 million times. So it's basically, it's doing a lot of polling. It's looking for more and more data. And then we can see how many times it called send message. This would have been for sending. This was like a read workload, so this is how many times it was, sending a command or sending a response back to the initiator. Readv would be, send message would be sending the data and the response back to the initiator. Readv would be getting the command from the initiator. We actually, Ben Walker and I were looking at some some NVMe TCP data several months ago and ran this script, and we found a bug in the SPDK code. We found a case where we were actually doing an extra read V in some cases when we didn't need to, and it was solely because of this. We could see how many IOs we were doing, and the read V count didn't match what we had expected, and so there's some real cases where we found some bugs that we could go fix with this type of analysis. Okay, so finally some tips and tricks. So first, so bpftrace probes the user space ones are expensive. So in the kernel, I mean it's using eBPF, so it's very fast in the kernel, but when it's in user space, there's actually a kernel trap that has to happen, and that's relatively expensive. I think Conrad Steiber did some measurements that it's around, depending on the architecture, of course, like up to 3 microseconds of overhead, which means that you can only capture maybe 300,000 user space probe points per second. So this is not suitable for IO path operations, really only control path. Now that doesn't apply for like the system call. All the system call trace points are in the kernel. Those are very, very low overhead, and those you can run in a performance workload without noticeably impacting performance. So there's also been some work. Conrad has done some really interesting work combining SPDK and BPF trace data. Where effectively you can annotate the SPDK traces with information from the BPF trace. So a common example here is, let's say we're capturing data for an NVMF RDMA workload, and so we have information about the NVMe host and the subsystem NQN, but we don't want to have to put those those long strings into each trace point event. That's just too much data, and that's going to have a lot of overhead. And so what Conrad demonstrated here, I've got the link. You'll be able to access this once the slides are posted. The link's there, but if you want to get access to this link later, you'll see it on the slides, is being able to capture the control path data with BPF trace and then supplement that data into the SPDK trace, so that then instead of just seeing, just some, this was some NVMF request, you can actually see this is an NVMF request that originated from this host and it was directed to this subsystem NQN. So that's super powerful. These circular history buffers, they're limited. You do have the ability to configure how big they are, but it's still a limit. If you want to capture these traces over a longer period of time, you just can't allocate shared memory files that are big enough. So Xiaodong Liu from the SPDK community created an application called SPDK Trace Record. And so what it does is you run this on the side. It's basically copying data from the shared memory file into another file, and it continues to run. So it's, while the SPDK application is capturing all this data, this other SPDK Trace Record app is stuffing it into a separate memory file. And so it allows you to capture a trace over a much longer period of time, which can be really useful. And then there's a lot more detail on how to define these SPDK trace points. I went, very roughly into the constructor function and how those things work, but Shishik Karas has posted on the blog a lot more details on this, and you can get that from the link here. So, hope you found this interesting. If you have any questions on SPDK Trace, you know where to find us on Slack or the mailing list. Hope you enjoy the rest of the summit. Thanks.